Hey friends, I'm Shaptarshi. I just completed my Masters in Chemistry from IIT Kanpur. And in this video series for IIT-JAM exam, I wanted to cover all the different types of numerical problems that come for physical chemistry. And by doing those problems, I'll be explaining the concepts as well. In physical chemistry IIT-JAM, 90% of your questions will be numerical based. So it's very important. And just like this video, I'll be making similar videos on different physical chemistry topics as well. So with that, let's get started with this one.
Friends, and today we will look at the second part of thermodynamics, which is very important, the Carnot heat engine. And over here, what we will do is we'll look at the concept, main concept that will be coming or might come in the exam, and some numericals that will be very, very important because Carnot's heat engine is a very important part of your thermodynamics and your IIT-JAM exam. So let us look into this concept. So Carnot heat engine, and the proposal that was given by Carnot was he wanted to see how much work is produced when a certain amount of heat is given. So it's a relation between work and heat, right? How much work is produced when a certain amount of energy or heat is given. And so for that, suppose we have a source from where the heat is coming, right? And this is an engine which is working and producing this work. And obviously any engine, there is some amount which is lost as heat, right? Lost as heat, and that goes to the sink. Suppose this is your Q2, right? So your work will be the amount your the amount that you have got, and the minus the amount that you have lost, right? So over here, I think there is a small glitch over here, that this will be Q1 minus Q2, right? So the amount of heat that you have got minus the amount of heat that that is lost. So this is the source minus the amount that goes to the sink or that is lost. And the main thing about Carnot heat engine is the efficiency. What is efficiency? This is efficiency, and efficiency is given by the work produced and divided by the heat supplied. So it calculates the output. So what is our work produced? So if you think what is the work produced, as I said, it is Q2 minus Q1. What is the heat supplied? It is by Q1. So this is nothing but this is eta is equals to Q2 minus Q1 divided by the heat supply, that is Q1. And if you like do the division of this, you will get this formula, 1 minus Q2 by Q1. This can also be written in the form of temperature, which is very important. You should know the different forms that efficiency can be written, because in the question they might not give the heat amount, right? They might not give the energy, but they might give the temperature, and you have to find from the temperature the amount of efficiency. And these problems are very easy, but sometimes the students don't do these topics. I don't know why, but it's very scoring, these topics, especially because nothing complex is asked, especially in the IIT-JAM level, from this topic, right? So we'll look at an example, very good example I have for you guys regarding this Carnot heat engine. But before going there, I'll talk about the Carnot cycle, which is the heat cycle. Remember, it's a P versus V graph. Nothing much to remember over here. Derivations and stuff that will take a long time, and that is not normally asked in the exam. What you need to know is that the curve looks like this, and the different portions, the AB and the CD. You see A, B, C, D. A, B and the CD portions, that those are isothermal and reversible expansion or compression. When it is the volume is increasing on this side, it is expansion. When we are going from C to D, the volume is decreasing, so it is compression, right? But you remember that AB and CD, these are isothermal, that means same temperature, and they're reversible, expansion or compression, right? And your BC and DA, the BC and DA, so if it is expanding, like the volume is increasing, it is expansion. If its volume is decreasing, it is your compression, right? It is adiabatic and reversible. The heat change is constant, right? So if you remember, guys, that the work done for this different process are different. I have explained all this in the previous thermodynamics part 1 video. Is that for isothermal and reversible, we will have your something like nRT ln final volume VF by the initial volume. This is the work done. And for the adiabatic and reversible process, we have this condition of PV to the power gamma equals to constant. So if we calculate all the work in these different areas, A, AB, your BC, CD and DA, the final total net work that we get, is this. Normally no numericals are normally asked from this Carnot cycle, but just for information I'm telling you if it is asked, because it is a bit important. So it is given by RT minus T prime, where T was the AB portion and T prime was the CD portion. And ln V2 by V1, where V2 was the volume at B and V1 was the volume at 1, right? So, and this formula comes after a lot of derivations. Okay, you have to calculate the work for every process and then use this condition of PV to the power gamma constant. So there's a lot of derivation to it, which if you have time you can see before the exam, but if you're just like trying to revise everything in a quick manner, you don't need to watch that, right? Because derivations are not normally asked in the exam. But if you remember this formula also, it's very good. And normally not questions are normally asked from this portion, but I've just for information I'm told you. But do remember the cycle. What is important? The cycle. It's a P versus V graph where it shows the total Carnot cycle, right? Okay, now we will see an example from our Carnot heat engine. It's a very good example which tests all the important criteria of this Carnot heat engine. So let us look at this problem, right? So as I always say, let us read the question line by line, take the information step by step, and let us proceed. Okay, no need to hurry. When you do a numerical, always do step by step. So as I always first say, first let us read Carnot engine working. So I wrote this question, B/W means between. It works between 0 degrees Celsius and 100 degrees Celsius. So the two temperatures are given, right? It takes up 840 joules from a high temperature reservoir. Okay, so now the heat is given. So as I always say, that first you write what is given, right? So what is given over here? Your the two temperatures are given. So the source always has a higher temperature in this Carnot heat engine. So this is set. It works with 100 degrees Celsius, and let us say the sink is 0 degrees Celsius. Okay. So yes, and the energy that is goes is so let us say Q1. That is Q1 is 840 joules from the high temperature. So I'm just writing height. So I've written all the information. Now I need to calculate the work done. So let us see how that we will do that. So let us just draw a rough diagram. Very easy to draw these diagrams. Let us say this is source. This circle is the engine. The work is produced over here. This is the sink. And so what it says, Q1 is 840 joules. So this is 840 joules is coming in. And the source temperature is how much? 100 degrees Celsius. So we can convert this to Kelvin also. If we calculate the difference of two temperatures, no need to convert to Kelvin. It's the same in Celsius and Kelvin. The difference is same. Okay. Otherwise, you can also convert to Kelvin if you want. So first we have to find the work, as they have said, right? The work done. Okay. So let us use this formula of efficiency. I'm just using the black pen for more clarity. Efficiency eta. What is that? It is the work supplied by the heat given, right? So let us say that is W. What is the heat that is supplied? That is 840 joules, right? What is the efficiency, or what is another form of efficiency that we know? We know it is 1 minus Q1 by Q2, right? And so where your what do you say? Where Q1 is the source and Q2 is the sink. Okay. No, over here it should have actually be Q2 by Q1. Okay, so sometimes I make the mistake. The trick over here is better than remembering 2 and 1. You remember which is source and which is sink. So that is the best way to remember all these things. So, and an easy way of remembering this is that efficiency will be a positive number, right? So if I say that it is Q1 minus Q2 divided by Q1, Q1 has to be the source because it is a higher temperature. So efficiency has to be positive. Okay, so that is a good way of remembering this formula. Or either you remember that this is your sink and Q1 is your source. Instead of remembering 1 and 2, which you can forget which is 1, which is 2, remember that efficiency will be positive term and which will be source and which will be sink. So let us do this formula. Okay, so eta is equals to, so you're seeing that the good thing about this is as I'm doing the problem, you can also experience how I'm tackling the problems that I'm facing, whether which is 1 or 2, which actually happens in the exam, right? You forget how the formula was related. So we have the concept of it. If you have the concept, now you can do the problem, even if you are forgetting some small things over here and there. So what is Q1 and Q2? So Q1 and Q2 is not given. So what did I say in the last, in just the previous minutes, is that this can also be written as your T2 minus T1, where your T2 is your sink and T1 is your source. So because the heat is not given, we will use the temperature. So this will be T1 minus T2 by T1. So T1 is how much? T1 is 100. So let me just do one thing, is let me just convert this to your what is a Kelvin. So this will be 373 Kelvin, this will be 273 Kelvin. So over here, if I'm writing it in terms of Kelvin, which we should do to avoid what silly mistakes, okay, or do not skip steps. Okay, sometimes we think, oh, it's so easy, we will do it right now, and without even calculating or writing anything, most probably in those problems we will make mistakes. Okay, so we don't need to show how smart we are, we need to get the right answer, that is our aim. So this will be 100 by 373. So that is your efficiency. So we got this, so no need to work out the total thing. So eta we got, and now we need to calculate the work. So in the third part, you see it was given, we have to find the efficiency. So we found the efficiency, which is 100 by 373. You do this by calculator. Okay, I don't have the calculator with me right now, so you can easily do that by calculator. And I will do this work done, which is so efficiency we got the answer for efficiency, and that is what's part 3 of the question. This is the answer. Please write in decimals, and I've always said at least write 2 figures after the decimal point. Okay, don't round off the first figure after decimal, right? At least 2 to 3 figures after the decimal. Okay, as precise as you can be. No need to write 4 or 5 figures, that is stupid. Okay, so let us calculate. Work done will be efficiency into the heat. So work will be, that is part 1, efficiency, which is 100 by 373 into heat, which is 340 joules. And so let me write what I did. It's eta into, I just replace the formula and make this a subject. So this is almost like this will be a bit less than 100, right? As you can see. Let me just see what the answer is given in the question over here. Is that okay? So they have actually calculated the answer in your ergs, which was not necessary really. Okay, I'm really sorry for this. I'm making a very silly mistakes. This is 840. Okay, so sometimes, as you saw, I wrote 340 actually. So guys, do the double check also when you're writing it. The question is that you're not writing the wrong number. I saw 840 and I wrote 340. Okay, that's why a good method, you know, of doing these questions is you do it in one page. Like they will give you a rough pad, right? They will give you a rough pad. You do it the numerical. If you have a big numerical, 2 marks numericals, you do it on one page total. Sometimes what happens, it happens with me also, is that when you turn the page, you go to the next page, now some of this data is in the previous page, and sometimes when transferring the data, you make silly mistakes like this, right? Instead of writing 340, you write instead of writing 840, you write 340. So what this will come is, so this will come around your 0.225 kilojoules. Okay, remember this, kilojoules, it's not in joules, answer is given in kilojoules. So this was in joules. Okay, so you do it and check whether it's coming or not, right? And let me know, or I'll just do it for you right now, or the video will go at a bit big actually. Okay, maybe you can comment in the comment box if the answer is not coming, but I think it should come. The heat rejected, that is Q2, right? If I'm taking Q1 as the source, so Q2 will be sink, right? So what did I say? That efficiency is given by 1 minus Q2 by Q1, also equals to 1 minus T2 by T1. So we can write that Q2 by Q1 is equals to T2 by T1. We know T2 by T1, we know Q1, we don't know, sorry, we know Q1, we don't know Q2, that is the heat is rejected. So let us just put the formulas and check. It's so simple, right? Q2, Q1 is what? 340, sorry, 340, it's 840 joules. Again making the same mistake. T2 was the sink. So T2 was 273 Kelvin. This is 373 Kelvin. So if you do this calculation, your Q2 should come around. The answer is given as, okay, they have given the answer in calories for some reason. Okay, so I don't know why they have converted the units. All of a sudden, it's a good practice for you guys also to change the units and see. So the Q2 answer that is given, that is in 146 calories. So I'll just do this second part for you, and check whether the answer is coming or not. So let me just use the virtual calculator only. Okay. Virtual calculator. So again, so this is another part you can make mistakes when you're transferring data from your notepad, your rough pad, to your calculator. You can again make a mistake over there, so be careful over here and do check it out whether you're not making a mistake, right? So this is your 273 divided by 373 into your 840, right? 840 joules. This is coming as 614 0.79, okay, whatever it is, right? And if I convert this to calories, I have to, yeah, I believe it is 1.987, right? No, it is 4.12, something like that, right? 4.12. I don't remember the exactly, but you guys should remember this. I think it's 4.2 or 4.12. So if I do 4.12, it's coming as 149. Okay. Okay, the answer is actually 146 that is given. I'll just check. 1 joule to calories. 1 joule to calories. How much it is? Let me do the opposite then. 1 calories to joule. It is 4. Okay, I said 4.12. So this is actually your 4184. So it is kilocalorie. So if you do this calories, so can you do this calories? Just do calories. No, it's gram calorie. 4.184. So I did 4.12. So it is 4.184. Remember this transformations. I will make a video for this, all these transformations that it's given, because sometimes they will ask in different units and you should know. So I'm a bit out of practice, but you guys should know all these units. But even then I said 4.12. So if you do 4. This, how much it was, 4.18, then you will get the answer as 146 calories, right? And you will get this answer. And this previous one you can also check, is that 840 by 373. I can also do this for you if you're not getting the answer. I'm just doing it. 100 into 840 by 373. 840 into, sorry, division. How is this backspace? So let me divide it right now by 373, and you have to make this in kilojoules. That if you make this in kilojoules, it will be 0.225. And what is the answer that is given? It is 0.225, right? So we got the answer. So this is how you guys do this formula for this is Carnot engine and the problems you do it. And just for your understanding and comfort, I showed you how to tackle the problems also, right? You guys were seeing how there were some options for silly mistakes I could have made, but how you avoided those silly mistakes. So please learn from those and please do not make all these things in the exam, guys. I am telling you this one secret. If you make less silly mistakes, I know it's very tough, but if suppose by an ideal situation, if you make no silly mistakes, right? I have analyzed this actually in my own time. If you make no silly mistakes, your chances for getting into IIT will increase like anything. Like, I'm really telling you, because there are many good students who also make silly mistakes. Everyone will make silly mistakes, but the guy who will make less silly mistakes, his admission will skyrocket. So all the best with that, because you guys know the things, you guys know it everything, but everyone will get emotional and do all those things. I'll make a video on how to avoid all these things. So, and in the next video I'll make about entropy, which is also very important. So with that, all the best. God bless you guys.